Good morning, everyone. My name is Thiago Pereira, and today I'll present the work that I've done during my master's about polymer flooding, adsorption, and oil displacement. Conventional oil recovery methods, such as water flooding, are very popular due to the simplicity and relatively low-cost operation, but the sweep efficiency of this technique is usually affected by the high mobility ratio between fluids that creates preferential paths on the porous media, leaving a huge amount of oil in the reservoir. Because of that, enhanced oil recovery methods have emerged as an attempt to optimize oil recovery operations. The addition of polymers to the injection water is one of the most used EOR methods because of the ability of these chemicals to increase the viscosity of the solution even at low concentrations, reducing the mobility ratio between fluids and resulting in a better oil displacement. However, there are many factors related to the use of this substance that can modify the original characteristics of the porous medium, such as polymer retention. There are two main types of polymer retention mechanisms, mechanical entrapment and adsorption. Both of them are illustrated in this figure. Mechanical entrapment occurs when large polymer molecules get trapped in narrow pore throats, and polymer adsorption is caused by the interaction between polymer molecules and the porous media walls. It depends on many factors such as the degree of hydrolysis, flow conditions, and the characteristics of the porous media, like permeability and the mineralogical composition. And in this case, the presence of clay in the porous media increases the amount of polymer adsorbed. Now, let's see how it occurs during the injection of polymer solution through a porous medium. As we have seen before, during the oil recovery process using water flooding, the high mobility ratio between fluids creates some preferential paths. The water tends to flow through these paths, producing a non-uniform sweep, and leaving a large area of the reservoir unswept. When polymer solution is injected, polymer retention mechanisms may occur, modifying the original characteristics of the porous medium. Mechanical entrapment and polymer adsorption will block some of these preferential paths, diverting the water phase to new areas of the reservoir, then increasing the sweep efficiency. So, in this example, we could observe an advantage of polymer flooding. But, on the other hand, if this blockage is not well controlled, it can result in a higher injectivity loss, or in a worst case scenario, it might result in the total blockage of the formation. So, the objectives of this work were to understand the retention effects caused by polymer solution in rocks with different characteristics, and to evaluate these effects on oil displacement tests using three different water compositions. For this, we did an experimental work in a core flooding system which consisted of adsorption tests and oil recovery tests. Let's talk about the adsorption tests. As I said, these tests were used to analyze how polymers interact with the formation. For this, we used three different core samples, gray Berea, buff Berea, and Bentheimer. The cores were chosen due to its variety in permeability and mineralogical composition, so we could study the effects related to these properties. Core samples were originally 12-inch length, and we divided it in three pieces of 4-inch for the test. So, one was used for adsorption tests, and the other two for recovery tests. Doing this, we could minimize huge alterations in core characteristics. About the fluids, we used a brine that mimics the formation water of a Brazilian oil field, and the polymer used was a hydrolyzed polyacrylamide AN125 VHM with a hydrolysis degree of 25% and a molecular weight of 10 to 12 million. Talking about the preparation of solutions we have. After preparation, part of the brine was diluted to 70% of its original concentration and used as injection water, and part was used to prepare the polymer solution. This salinity conductivity difference was used as water tracer. Polymer solutions were prepared according to the recommended practice 63 of API. This solution behaves as a non-Newtonian fluid, what means that the fluid viscosity depends on the shear rate. Because of that, we had to calculate that shear rate applied to the solutions inside of each core, using the Christoffel and Middleman equation, then calculate fluid viscosity. Besides that, after preparation, all solutions were bubbled with argon in order to minimize the dissolved oxygen, avoiding polymer degradation. This is the experimental setup used. Fluids were placed outside the oven to reduce degradation. Two thermosetting loops were set upstream the core holder to ensure that fluids entered the porous medium at test temperature. A core filter was used upstream the core sample to ensure that the polymer solution does not contain any lumps that may plug the pore space. And downstream the porous medium, there were a conductimeter to identify fluids interface and a system of capillary tube that worked as a capillary rheometer to measure fluids viscosity. And test conditions are shown on bottom right. Adsorption tests were carried out using the two Slugs method. This method was first used by Lodge in 1985 to measure the effect of inaccessible pore volume on polymer solution core flooding experiments, and consists of two polymer slugs interposed by water flooding. Firstly, the core saturated with brine and its initial permeability is measured. Then, slug number 1 is injected, and this phase is responsible for almost all polymer adsorption. After that, another water flood is performed to remove all the non-adsorbed polymer from porous medium. Then, slug number 2 is injected. Here, it is supposed to occur minimal or no adsorption. And finally, we do the last water injection to rinse the core again and determine its final permeability. The alternation of water phases flowing through the conductivity meter and the capillary tubes generates polymer and trace breakthrough curves as function of injected pore volume. The data were normalized as function of fluid concentration. So at 0 we have initial concentration, that means only brine flowing, and at 1 we have final concentration, that means only polymer solution flowing. As we can see on the graph, there is a shift between curves that is caused by retention mechanism. When we inject the first slug of polymer, the polymer molecules will saturate the porous medium walls and block some of the pores. As the pore surface was completely saturated with polymer, the second slug passes through the porous medium with no significant new adsorption. Then, this solution is noticed earlier by the measurement system located downstream the core. Using these curves, we can calculate the inaccessible pore volume and the mass of polymer adsorbed. The difference in pore volume between conductivity curve and slug number 2 at the inflection point gives the inaccessible pore volume, and the difference between slugs number 1 and number 2 at the inflection point again gives the volume of polymer solution corresponding to the mass of polymer adsorbed. The resistance factor and the residual resistance factor are also parameters that can be determined by this methodology. RF gives alterations in mobility ratio caused by polymer injection, and RRF gives alterations on porous medium permeability. So here are some results of polymer adsorption tests. These tests showed a strong relationship between retention mechanisms, core permeability, and mineralogical composition of porous medium walls. On the left, we have data of concentration and conductivity as function of injected pore volume. And on the right, we have data of delta P across the core sample as function of injected pore volume as well. These first results are of gray Berea that has a low permeability, and core sample with this property presented high levels of polymer retention, and it is believed that it was mainly caused by mechanical entrapment. As we can see on the right, there was no pressure stabilization during slugs number 1 and number 2. So that indicates that the polymer molecules were probably being filtered by the narrow pore throat of these low permeability core samples. These are results of both Berea, another core with low permeability but with a higher clay content. Here we can see almost the same retention trends of the previous one, but there is something interesting here. This core has a higher permeability than the gray Berea, but the amount of polymer retained was higher. And we believe that it may be caused because of the mineralogical composition of this sample. For the Bentheimer, in which permeability is higher, results were good. It seems that there was no mechanical retention since the stabilization of delta P across the core was achieved during slugs number 1 and number 2. So now we'll talk about the oil recovery test. 3 different water compositions were used: brine, glycerol water solution, and polymer solution. Brine was used to have an initial correlation between cores. Glycerol was used to produce a water phase with an equivalent viscosity of the polymer solution. We did this to isolate viscous effects during oil recovery tests, so we could better analyze the retention mechanisms since the glycerol water solution does not adsorb on porous media walls. The fluids used were the same brine, same polymer solution, glycerol water solution, and the oil Agicon 500 PS. To achieve an equivalence in viscosity between glycerol water solution and polymer solution, we used Christoffel-Middleman equation to determine the shear rate inside the cores. Then, it was compared to measurements of these solutions on the rheometer. By doing that, we could calculate the amount of glycerol and brine to produce each test solution. For this work, 2 different oil recovery protocols were developed. The first was performed with brine and glycerol water solution. First, we saturated the core with brine and calculated its permeability. Then, we injected oil and calculated the saturation of each phase. And then, we did the first oil recovery using water flooding. After that, we injected oil again to establish a new initial condition of the reservoir and recalculate each phase saturation. Then, a slug of 4 part volume of glycerol water solution was injected and displaced by brine. For protocol number 2, we did the same steps, but instead of using glycerol water solution, we used polymer solution. So these are the results of oil recovery tests for gray Berea core samples. The graph on the left shows results of protocol number 1, and on the right, results of protocol number 2, both in terms of oil recovery factor as function of injected pore volume. Here, we can see the amount of glycerol used to produce a solution with an equivalent viscosity of the polymer solution. It can be noticed that recovery factors using brine are pretty close to each other, so the idea to use it as an initial correlation worked, and improvements in oil recovery factor was almost 2 times higher using polymer solution. Here are the results for both Berea core samples, and as we can see, results showed almost the same trend of gray Berea. Finally, these are results for Bentheimer core samples. Note that recovery factor using water flooding were already very high, around 50%. So improvements using IOR methods were not as significant as they were for previous tests. And this slight variation may be included on uncertainties of measurements. However, in both protocols, one noticed a production anticipation that may be very interesting for the economic point of view. The results of all tests are presented in this table. Here, we can better analyze the relationship between polymer retention, core permeability, mineralogical composition, and inaccessible pore volume. As lower was the permeability, higher was the retention. As higher was the clay content, higher was the retention. And as higher was the retention, higher was the inaccessible pore volume. The influence of polymer retention in oil displacement tests was stronger in low permeability cores. So it means that the permeability has a higher influence on polymer retention when compared to mineralogical composition. To better understand the effects of mineralogical composition, we are running static adsorption tests. On this test, we are measuring the capacity of each rock used to adsorb polymer molecules on static conditions. For this, we slice the core in small pieces, take it to a tank filled with polymer solution, and measure the variation of core weight. These are just preliminary results. We are adjusting the methodology, and later we need to normalize it by its surface area exposed to the solution and by its core dry mass. So, as final remarks, we have seen the polymer retention effects on rocks with different characteristics, analyzing the core permeability and the mineralogical composition. Also, the suitability of the two slugs methods for rocks with low permeability due to the occurrence of mechanical entrapment. The improvements in oil recovery factor using polymer solution was almost 2 times higher than using glycerol water solution, and it may be caused by polymer retention and viscoelastic effects. And as future work, we intend to use larger cores to check the relationship between core injection phase and injected pore volume and analyze delta P over different sections of the core sample. Also, try to isolate viscous, viscoelastic, and retention effects. And finally, work with alterations in the zeta potential of porous medial walls. I would like to thank the lab manager Felipe Lopes for all the help and Professor Márcio Carvalho for the opportunity to develop this work and for advising me. And also the LMMP team, my university, Pontifícia Universidade Católica do Rio de Janeiro, CAPS and Equinor for funding, the National Agency of Petroleum, Natural Gas and Biofuels, and the SPE members that are working on this student paper contest. Thank you very much.